Hi, my name is Kimani Nania, and this is my Physics Lab 5. So to introduce the lab, Faraday's law relates the time-varying magnetic field to an electric field. And the path is a closed path, and it's not zero, but it produces an EMF that creates a current. This current then can produce a magnetic field, which then produces a magnetic force on a system. And in our lab, the source of the electric field comes from the roll of aluminum foil, and the system is the magnet. So the purpose of the lab is to observe the average time the bar magnet takes to fall through the foil tube, model this interaction computationally through code, and compare this to the observations to determine the accuracy. And the results were the observed average time is 1.58 seconds, while the computational is 1.65. So the models used are Faraday's law, the Biot-Savart law, Ohm's law, magnetic force, and all their equations are seen on the right, which I'm sure we're all familiar with. And as you can see on the Faraday's law equation, this is kind of similar to our experiment, except the magnet will be turned the other way. The south pole end should go in first in our experiment. And the assumptions in our experiment were that no other forces acting on the magnet except the magnetic force produced by the roll of aluminum foil and gravity. So the experiment, as said earlier, was a magnet was dropped through a roll of foil, making sure the north end was pointed up, and the time it took to fall through the foil was timed, and we did this 5 times and averaged it out. The initial conditions included the bar magnet and the foil paper were both with independent fields. The width of the tube, the radius of the tube, the length of the tube, all their numbers are listed below. And the system is the bar magnet, the surroundings is the foil paper, and gravity. So in the code, this lab had a bunch of code, so we're just going to do a short summary. On the top right, you can see that's how you calculate the magnetic flux. And on the bottom left, this was how I calculated the magnetic field of the bar magnet, because once again, it had its own magnetic field just like the foil did. And on the bottom right, this is how you calculate the gravitational force on the magnet, the magnetic force, and the magnetic flux. Also, to calculate the current in the ring, because we all know the ring's current is what pushes the magnetic force. So my computational average was close to my observed. In the code, it was 1.65 seconds, but 1.58 in my observations. So they're super close, but the computational was slightly larger, meaning that the code was slightly slower. And in physics terms, this means that the bar magnet was more affected by the magnetic force in the computational model, meaning I likely calculated a higher force. And this is why I spent slightly longer in the tube. And sources of error could have came from lack of accounting air resistance in the calculations and timing error of the observations. So to conclude, the first what if question is, if the resistance was close to zero, this means the current would be at its maximum level. So this means that the magnetic force will in turn increase maximally. Thus, the magnet will fall through the tube slower and may even take an extremely long time to come out. And the second what if question, if there were holes in the tube, this means that the current will be missing parts of itself, so the current will decrease, and the decreased current will lead to a lower magnetic force, so the magnet will fall through the tube at a faster rate. Thank you so much for listening.